It's a funny thing, the dark. We spend a good portion of our lives in it. Yet, for centuries, we've done everything in our power to conquer it. We've tamed fire, invented the light bulb, and built cities that blaze with such ferocious intensity they create a permanent artificial twilight, blotting out the very thing the darkness was meant to reveal. We've walled ourselves off from the night. But if you can manage to escape that electric glare, to find a place on a moonless night where the world falls away into true deep black, and you tilt your head back, you'll see it. The oldest story ever told. It's a story written in pinpricks of light, scattered across an endless velvet canvas. It's a story that has been read by every human who has ever lived, from the very first of our kind to leave footprints in the volcanic ash of Laetoli, to the astronomers in their climate-controlled domes, peering through instruments that are, in essence, just more powerful sets of eyes. It's the story of the stars, which is, in the end, the story of us. Our relationship with those distant fires has defined who we are, where we believe we come from, and where we think we're going. It's a love story, a mystery, a family drama, and an epic adventure all rolled into one. And like all the best stories, it begins in the dark with a flicker of curiosity and a profound sense of awe. This is the story of astronomy, a new episode from our series, The Human Odyssey from English Plus Podcast. Imagine for a moment that you are not you. You are not living in the 21st century with a supercomputer in your pocket and the sum of human knowledge a few taps away. Instead, you are huddled around a crackling fire somewhere on the plains of Mesopotamia 10,000 years ago. The world beyond the firelight is filled with unseen dangers. The glinting eyes of a predator, the whisper of a rival tribe on the wind. The fire is your anchor, your small, precious island of warmth and safety in a vast, indifferent wilderness. But then you look up. Above you, the sky is not the hazy, light-polluted dome you know. It is a revelation. It is a riot of stars, a spill of diamond dust on black silk. The Milky Way isn't a faint, ghostly smudge you might glimpse on a camping trip. It's a brilliant, textured river of light, a celestial backbone so bright it seems you could almost reach up and touch its shimmering surface. You see constellations, not as the faint connect-the-dot puzzles of today, but as vivid, blazing pictures that leap out from the darkness. You don't know what they are, these points of light. They are as mysterious and powerful as the rising and setting of the sun, the waxing and waning of the moon, the turning of the seasons. But you are a human, and humans are, above all else, pattern-seeking, storytelling creatures. You notice that the sky is not static. Night after night, you see the same patterns wheeling overhead in a slow, majestic, and utterly predictable dance. You see a particularly bright star that appears just before the dawn at a certain time of year, and you notice its appearance coincides with the annual flooding of the river, the lifeblood of your small community. You learn to watch for it. That star becomes a herald, a messenger from the heavens, a sign that it is time to move to higher ground or prepare the fields for planting. You give it a name. You tell stories about it. Maybe it's a god, or the eye of a great celestial beast. The patterns in the stars become the forms of heroes, animals, and mystical creatures. The sky becomes a canvas for your imagination, a place to project your hopes, your fears, and your attempts to make sense of a world that often seems chaotic and arbitrary. This celestial storytelling wasn't just entertainment. It was a cognitive tool for survival, a way to remember and transmit vital information across generations. This was the birth of astronomy. It wasn't a science, not in the way we think of it today. It was a practical necessity, a calendar, a clock, and a compass all rolled into one. For the ancient Babylonians, the meticulous observation of the heavens became a state-sponsored enterprise. From their ziggurats, priest astronomers tracked the movements of the planets, which they saw as wandering stars. The word planet comes from the Greek planetes, meaning wanderer, believing they were omens from the gods that could predict the fate of kings and empires. They created the zodiac, dividing the sun's path into 12 equal parts, and kept centuries of detailed records on clay tablets, a comprehensive catalog of constellations and celestial events. This vast dataset, compiled for astrological purposes, would become an accidental and priceless gift to future generations of astronomers. In ancient Egypt, the star Sirius, which they called Sopdet, was the focus of intense observation. Its heliacal rising, the day it first becomes visible above the eastern horizon just before sunrise after a long period of invisibility, coincided with the annual inundation of the Nile. This event was the very cornerstone of their civilization, bringing fertile silt to their fields and ensuring a bountiful harvest. The entire Egyptian calendar, and thus their entire society, was built around this celestial alignment. The pyramids themselves, those monumental tombs of the pharaohs, were aligned with breathtaking precision to the cardinal points and certain stars, a testament to how deeply the heavens were woven into their worldview of Mu'at, or cosmic order. Temples like Karnak were designed so that on the winter solstice, the rising sun would send a beam of light deep into the sanctuary, illuminating the statue of a god. The sky was not just a clock, it was a temple. Across the globe, other cultures were having their own conversations with the sky. In China, court astronomers kept meticulous records of guest stars, sudden bright apparitions that we now know were supernovae. In the Americas, the Mayas developed a calendar of stunning complexity and accuracy based on long, patient observation of the sun, moon, and Venus. The ancient Greeks, however, took a different approach. While they too saw gods and heroes in the constellations, Zeus, Orion, Andromeda, they were among the first to try and understand the cosmos not just as a realm of divine whim, but as an ordered, rational system, a cosmos. Thinkers like Pythagoras and his followers proposed that the universe was governed by the elegant logic of mathematics and geometry. They imagined the Earth as a perfect sphere, and the planets moving in perfect circles, creating a celestial harmony, a music of the spheres that was inaudible to human ears but was the very definition of cosmic perfection. It was in the Greek world that the first comprehensive scientific model of the universe was born. It came from the mind of Claudius Ptolemy in the 2nd century AD. Living in Alexandria, the intellectual capital of the ancient world, Ptolemy synthesized centuries of Greek and Babylonian observations into a single coherent system. In his universe, the Earth was the stationary center. This made perfect intuitive sense. After all, we don't feel the Earth moving beneath our feet. The sun, moon, and planets moved around it in a complex system of circles called deferents. And upon those circles, the planets themselves moved in smaller circles called epicycles. It's easy for us, with our modern knowledge, to scoff at the Ptolemaic model. A geocentric universe? How quaint, how arrogant. But to do so is to miss the genius of it. Ptolemy's system was not just a guess. It was a sophisticated mathematical model that, for the most part, worked. It could explain the strange retrograde motion of planets like Mars, where they appear to temporarily reverse course in the sky, and could predict their positions with remarkable accuracy. It was a triumph of ancient science, and it would dominate Western thought for the next 1400 years. For over a millennium, humanity looked up at the sky and saw Ptolemy's universe, a cozy, human-centered cosmos, with Earth at its heart and the heavens revolving around us in a divinely ordained, perfect dance. It was a beautiful, comforting story, and for 14 centuries, it was enough. But the universe is patient, and eventually, cracks began to show in the elegant facade. For 14 centuries, the Earth stood still. The sun rose and set, the stars wheeled overhead, and the authority of Ptolemy, Aristotle, and the Church, which had masterfully woven the geocentric model into its own theology, was absolute. To question the Earth's central place was not just a scientific error, it was heresy. It was to question the very order of God's creation, to challenge humanity's special place in the universe. The cosmos was a neat, tidy hierarchy with God in heaven, humanity on earth, and hell below. To move the Earth was to shatter this entire framework. Into this silent, ordered cosmos stepped a quiet Polish cleric named Nicholas Copernicus, a man who wasn't looking for a revolution, but for a nagging sense of order the universe refused to provide. Copernicus was not a firebrand revolutionary. He was a meticulous scholar, a doctor, a diplomat, and a canon of the church. He spent decades poring over the ancient texts and wrestling with the ever-increasing complexity of the Ptolemaic system. To make the predictions match the ever more accurate observations, astronomers had to keep adding more and more epicycles, equants, and other mathematical fudge factors, turning the elegant music of the spheres into a clunky, dissonant mess. Copernicus, a man who appreciated simplicity and elegance, felt there had to be a better way. He found inspiration in the rediscovered writings of ancient Greek like Aristarchus of Samos, who had proposed a heliocentric model 2,000 years earlier. Copernicus's radical, almost unthinkable idea was to switch the positions of the Earth and the Sun. What if the Sun was the stationary center and the Earth was just another planet spinning on its axis once a day and orbiting the Sun once a year? This was the heliocentric model. Suddenly, the complex motions of the planets became beautifully simple. Retrograde motion was no longer a real movement of the planet, but an illusion created as the faster-moving Earth overtook a slower-moving outer planet, like a car passing another on the highway. Copernicus worked on his theory in secret for over 30 years, terrified of the ridicule and condemnation it would bring. He circulated his ideas only among a small circle of trusted friends in a short manuscript called the Commentariolus. It was only through the persistent efforts of his young protege, Georg Joachim Rheticus, that he was finally persuaded to publish his masterwork, De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres. The book was finally published in 1543, and the story goes that Copernicus was handed the first printed copy just hours before he died, a fittingly quiet end for a man who had, with the stroke of a pen, set the Earth in motion and demoted humanity from the center of the universe to a cosmic suburb. Copernicus's book did not, at first, cause the earthquake he had feared. It was dense, mathematical, and written in Latin. A preface added by a nervous publisher without Copernicus's consent suggested that the model was merely a mathematical convenience, not a description of physical reality. But the seed had been planted. The idea was out there, a whisper of dissent in the halls of academia. Before that whisper could become a roar, however, another crucial piece of the puzzle fell into place thanks to the obsessive work of a German astronomer named Johannes Kepler. Kepler, working with the unparalleled observational data of the Danish astronomer Tycho Brahe, discovered that planets do not move in perfect circles, as Copernicus had believed, but in ellipses. This finally allowed the heliocentric model to predict planetary position with an accuracy that the Ptolemaic system could never match. The stage was now set for a brash, brilliant, and confrontational Italian to turn the whisper of Copernicus and the mathematics of Kepler into a shout that would be heard across Europe. His name was Galileo Galilei. Galileo was everything Copernicus was not. He was a showman, a brilliant writer in the Italian vernacular, not Latin, and a master of self-promotion. In 1609, he heard rumors of a new invention from Holland, a spyglass that could make distant objects appear closer. With his characteristic ingenuity, Galileo didn't just copy the design, he improved it, building a telescope that could magnify objects 20 times. And then, he did something that no one had ever systematically done before. He pointed it at the sky. What he saw through that tube of wood and glass would not just challenge the old universe, it would shatter it. He looked at the moon and saw that it was not a perfect celestial orb of ethereal substance, but a world covered in mountains and valleys, craters and plains, just like the Earth. He looked at the Milky Way and saw that it was not a celestial cloud, but a vast, dense collection of innumerable individual stars. He looked at Jupiter and saw four tiny points of light orbiting it, moons. Here was undeniable visual proof that not everything in the heavens revolved around the Earth. He observed the phases of Venus, seeing it go from a crescent to a full disk, something that was impossible in the Ptolemaic system, but perfectly explained if Venus orbited the Sun. Galileo published his findings in a short, explosive book called Sidereus Nuncius, the Starry Messenger. It was an instant sensation, and it made him a celebrity. But it also made him powerful enemies. His discoveries were a direct physical challenge to the Ptolemaic model and the authority of the Church. The cozy, Earth-centered universe was crumbling, and the powers that be were not going to let it go without a fight. The story of Galileo's trial is one of the greatest dramas in the history of science. In 1633, he was summoned before the Inquisition in Rome. It was a clash not just of ideas, but of personalities and politics. Under threat of torture, the aging, infirm astronomer was forced to recant his support for the Copernican system. He was placed under house arrest for the rest of his life, a prisoner in his own home. Legend has it that as he rose from his knees after his recantation, he muttered under his breath, "Eper si move," which means, "and yet it moves." The story is probably apocryphal, but it captures the spirit of the man and the moment. The Church could force Galileo to be silent, but they could not stop the Earth from moving. The telescope had opened a window onto a new universe, and there was no closing it. The revolution had begun. While Galileo had shown that the planets moved in a sun-centered system, and Kepler had described how they moved in ellipses, it was another towering figure who would explain why they moved. If Galileo was the rebel, Isaac Newton was the architect, the man who would provide the laws that governed the new Copernican cosmos. Newton, born the year Galileo died, was a strange and solitary genius. He was a man of intense, almost obsessive focus, capable of incredible feats of concentration, but also prone to fits of rage and bitter disputes with his scientific rivals. The story of the apple falling from the tree is likely another myth, but it contains a kernel of profound truth. Newton's great insight, his aha moment, was to realize that the force that pulled the apple to the ground was the exact same force that held the moon in its orbit around the Earth and all the other planets in their orbits around the sun. It was a breathtaking leap of intuition. For millennia, the heavens and the Earth had been seen as two separate realms, governed by different laws and made of different substances. The terrestrial realm was one of change, decay, and imperfect straight-line motion. The celestial realm was one of perfection, eternity, and perfect circular motion. Newton, with a single idea, united them. The celestial and the terrestrial were one and the same, all subject to a single universal law of gravitation. In 1687, he published his Philosophiae Naturalis Principia Mathematica, or Mathematical Principles of Natural Philosophy, arguably the most important scientific book ever written. In that book, he laid out his three laws of motion and the law of universal gravitation. With a few elegant mathematical equations, Newton could explain and predict the orbits of the planets, the paths of comets, the rhythm of the tides, the trajectory of a cannonball, the entire machinery of the cosmos. The universe, in Newton's view, was a vast, intricate clockwork mechanism set in motion by God, but running according to predictable, discoverable laws. It was a universe that could be understood through reason and mathematics. The gods and omens of the ancient world were gone, replaced by the elegant precision of physical law. The new understanding gave humanity a sense of power and optimism. If we could unravel the secrets of the heavens, what else could we achieve? The Enlightenment, the age of reason, was in full swing, and Newton's clockwork universe was its emblem. For the next 200 years, astronomers worked within the Newtonian framework, refining their measurements, discovering new planets like Uranus by William Herschel in 1781 and Neptune, predicted mathematically before it was seen, a stunning confirmation of Newton's theory, and cataloging the stars. They built bigger and better telescopes. For the first time, in 1838, they were able to measure the distance to a star using parallax, proving that the Sun was just one of countless others scattered across unimaginable distances. The universe was getting bigger, but it was still a familiar, comfortable place, a well-behaved system running on Newtonian time. But at the turn of the 20th century, a few cracks began to appear in Newton's magnificent edifice. Certain observations, like the strange orbit of Mercury, couldn't quite be explained by his laws. And a young planet clerk in Bern, Switzerland, was about to blow those cracks wide open. Albert Einstein, like Copernicus, was a quiet revolutionary. In 1905, his miracle year, he published a series of papers that would fundamentally change our understanding of space, time, and gravity. Newton had imagined space and time as a fixed, absolute, unchangeable stage on which the drama of the universe played out. Einstein showed that this was not the case. Space and time were not separate, but were woven together into a single, four-dimensional fabric, space-time. And this fabric was not a passive backdrop, it was an active participant in the cosmic drama. It was curved and warped by the presence of mass and energy. Think of it like a stretched rubber sheet. A bowling ball placed in the center will create a deep dimple. A marble rolled nearby will not be pulled toward the bowling ball by a mysterious force, but will simply follow the curve in the sheet created by the ball. This was the heart of his general theory of relativity, published in 1915. In Einstein's universe, gravity was not a force, but the result of geometry. The Earth orbits the Sun not because it is being pulled by an invisible rope, but because it is following the straightest possible path through the curved spacetime created by the Sun's immense mass. It was a mind-bending, weird, and beautiful idea, and it made a series of predictions that could be tested. One of those predictions was the light itself should be bent by gravity. In 1919, during a solar eclipse, the English astronomer Arthur Eddington led an expedition to photograph the stars near the Sun's edge. His measurements confirmed Einstein's prediction precisely. The news made Einstein a global superstar overnight. Newton's clockwork universe had been replaced by something far stranger and more wonderful: a dynamic, flexible, relativistic cosmos. But Einstein's theory had another, even more profound implication. His equations suggested that the universe could not be static. It had to be either expanding or contracting. Einstein himself found this idea so philosophically repugnant that he added a cosmological constant to his equations to force the universe to be static and eternal. It was, he would later say, his biggest blunder. Because the universe was expanding, in the 1920s, an American astronomer named Edwin Hubble, a former lawyer and boxer, using the giant 100-inch telescope on Mount Wilson in California, made two of the most important discoveries in the history of science. First, he settled what was known as the Great Debate about the nature of the fuzzy spiral nebulae. By identifying a special type of pulsating star called a Cepheid variable, whose properties had been discovered by the astronomer Henrietta Leavitt, one of the female computers at Harvard, Hubble was able to measure the distance to the Andromeda Nebula. He found it was nearly 1,000,000 light-years away, far outside our own Milky Way. These nebulae were in fact entire galaxies, just like our own, island universes. In an instant, the known universe expanded by a factor of billions. Our galaxy was not the universe. It was just one island in a vast cosmic ocean. Hubble's second discovery was even more staggering. By analyzing the light from these distant galaxies, he found that their light was shifted toward the red end of the spectrum, a phenomenon known as redshift, similar to the way the pitch of a siren drops as it moves away from you. The redshift meant the galaxies were all moving away from us, and the farther away a galaxy was, the faster it was receding. The universe was expanding, just as Einstein's original equations had predicted. If the universe is expanding, then it must have been smaller in the past. If you run the clock backward, all of those galaxies rush back together until at some point, everything in the universe, all matter, all energy, all of space-time itself, was concentrated into a single, infinitesimally small, infinitely hot and dense point. This was the birth of the Big Bang Theory, a name coined derisively by its chief opponent, Fred Hoyle. The universe was not eternal. It had a beginning. Some 13.8 billion years ago, it exploded into existence, and it has been expanding and cooling ever since. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, accidentally discovered the faint leftover heat from that initial explosion, the cosmic microwave background radiation, the echo of creation. They had been trying to eliminate a persistent hiss in their radio antenna, even cleaning out pigeon droppings, before realizing they had stumbled upon the afterglow of the Big Bang. The evidence was undeniable. We were living in the aftermath of a cosmic cataclysm. The 20th century had given us a new creation story, a scientific one, but one no less awe-inspiring than the myths of old. We had a timeline for the universe, an understanding of its scale, and a theory for its origin. But there were still so many questions. What did the early universe look like? How did the first stars and galaxies form from the primordial soup? What happens in the violent hearts of quasars and the mysterious depths of black holes? And what is the ultimate fate of the universe? To answer these questions, we needed a new eye, one that could see more clearly than any telescope on Earth. Our planet's atmosphere, the very air we breathe that protects us from cosmic radiation, also blurs and distorts the light from distant stars. To get a truly clear view, we had to go above it. We had to put a telescope in space. The idea for a space telescope had been around for decades, but it was an incredibly ambitious and expensive undertaking. After years of planning, lobbying, and construction, the Hubble Space Telescope was finally launched aboard the Space Shuttle Discovery in 1990. It was the culmination of a dream, the most sophisticated astronomical instrument ever built. And at first, it was a catastrophic failure. The first images that came back were blurry, a fuzzy mess. A tiny, almost imperceptible flaw in the telescope's main mirror, a mistake smaller than the width of a human hair, had turned the billion-dollar project into a national embarrassment. It was a heartbreaking moment for the thousands of scientists and engineers who had dedicated their lives to the project. But NASA did not give up. In 1993, in one of the most complex and daring space missions ever attempted, a team of astronauts flew to the Hubble, captured it with the shuttle's robotic arm, and performed a series of grueling spacewalks to install corrective optics, essentially giving the telescope a pair of perfectly prescribed glasses. And it worked. The blurry images sharpened into a focus of breathtaking clarity. And with that, a new era of discovery began. The images that Hubble had sent back to Earth over the past 3 decades have transformed not just astronomy, but our entire culture. They have become modern icons, revealing a universe more beautiful, more violent, and more strange than we had ever imagined. We have seen the pillars of creation, towering columns of gas and dust where new stars are being born. We have seen galaxies colliding in a slow, graceful dance of gravitational destruction and renewal. Most profoundly, astronomers pointed Hubble at a patch of sky that seemed completely empty, no bigger than a grain of sand held at arm's length. For 10 straight days, it gathered the faintest specks of light. The resulting image, the Hubble Deep Field, revealed not emptiness, but over 3,000 galaxies, each one a home to billions of stars. We were seeing back in time, to the very edge of the observable universe. Hubble has helped us to measure the age of the universe with unprecedented accuracy, to confirm the existence of supermassive black holes at the center of nearly every galaxy, and to discover that the expansion of the universe is not slowing down as expected, but is actually accelerating, driven by a mysterious force we call dark energy. It has shown us that the planets of our solar system are not unique. There are countless other worlds orbiting other stars, some of which may even be habitable. And it has helped confirm the existence of dark matter, an invisible substance whose gravity seems to be holding galaxies together, a discovery pioneered by the patient work of astronomers like Vera Rubin. Together, dark matter and dark energy make up 95% of the universe. The grand, star-woven story we had been reading for millennia, it turned out, was written with only 5% of the available ink. Well, my friends, the story of astronomy is a story of ever-expanding horizons and ever-deepening humility. It began with our ancestors looking up at the night sky, trying to find their place in the cosmos. They placed themselves at the center of a small, cozy universe with the heavens revolving around them. Copernicus and Galileo kicked us out of the center, placing us on a small planet orbiting a mediocre star. Edwin Hubble showed us that our galaxy is just one of hundreds of billions, adrift in an ocean of space-time so vast it is beyond our ability to truly comprehend. And yet, with each step that has seemingly diminished our cosmic importance, we have gained something far more valuable: a deeper understanding of the universe and our intimate connection to it. The iron in our blood, the calcium in our bones, the oxygen we breathe, every atom in our bodies, save for the primordial hydrogen, was forged in the thermonuclear heart of a dying star billions of years ago. We are, as the astronomer Carl Sagan so eloquently put it, made of star stuff. We are the universe's way of knowing itself. And the story is far from over. The James Webb Space Telescope, Hubble's successor, is now peering even deeper into the infrared, showing us the universe in a new light, revealing the hidden nurseries of stars and the atmospheres of different exoplanets. We are on the verge of being able to search for biosignatures, the chemical signs of life on other worlds. The questions we are asking are the same ones our ancestors asked around their campfires 10,000 years ago. Are we alone? What is our place in the universe? We don't have all the answers, of course. We probably never will. But the quest itself, the act of looking up in wonder and asking questions, is what makes us human. The story of astronomy is the story of our insatiable curiosity, our relentless drive to explore, to understand, and to find our place in the grand star-woven tapestry of the cosmos. It is the longest and most epic of all human adventures, and the next chapter is just beginning. With that, my friends, we come to the end of our very special story of astronomy for today. I really hope you enjoy listening to it as much as I enjoyed writing it and reading it, to be honest. And with that being said, I would like to thank you for your time, the time you gave me listening to this story. I hope this added something to your knowledge and, of course, entertained you along the way. I'm Danny, and this is English Plus Podcast, and this is the end of another episode from our series, The Human Odyssey. I hope you enjoyed it. And remember, if you want to unlock access to all my episodes, you can do that by subscribing to English Plus Premium on Apple Podcasts or on my Patreon page. Thank you very much for listening. And remember, always look up and never stop learning with English Plus Podcast. I'll see you next time.